This problem builds on the prior one where we calculated the effective distributed force along the blade that's been spinning. Now we're going to calculate out the effective internal force at a distance along this blade that is spinning. So we'll recall that we calculated more or less using the principle of equilibrium, except we didn't actually write the algebraic equation for equilibrium. That's what we're going to do now. We instead were just thinking about, okay, there's got to be a distributed force along this blade that is acting equally and opposite to an internal force, P. And this is what we calculated in question 3 for the distributed force. So we know that it's dependent on the density, the angular velocity squared, this quantity L minus x, and A. For the internal force, what do we do? Well, we're just going to integrate this distributed force with respect to x. This has units, what is this? The distributed force has units of newtons per meter, and we're going to integrate that distributed force with respect to x, and then be able to calculate the internal force like we see here. And so the resulting internal force is this expression that we have, rho omega squared A times quantity Lx minus 1/2 x squared. Let's go ahead and implement this problem in Colab. Last time we did some work in Google, but because now these problems are building up, it's probably nice if we go ahead and have a script that will be able to keep using and extending. So we're going to import numpy as in p, and the parameters we are going to be using include density. So we'll do a rho, and that rho is 1,000. Okay, so 1,000, and it's going to be kilograms per meter cubed. Okay. We'll also have an acceleration that will be omega squared times quantity L minus x. So, well, actually, no, we're going to use the angular velocity there, right? Because we have an expression that doesn't have the final result in terms of an acceleration, but it's in terms of the angular velocity. So let's just define omega. And omega is going to be 101 radians per second. So 101, and we'll just do radians per second. Remember, radians is kind of a unitless quantity, and well, this is already per second, so we're just leaving it like that. Cross-sectional area. For that, we have 2.9 centimeters squared. So 2.9 centimeters squared. So we're going to need to multiply by, well, we can do it this way. 1 e to the minus 4, or I could have just done e to the minus 4, and that gives us meters squared from centimeters. The length is going to be given by 1.2 meters, so we have that here. And we're at an x of L over 2. So x is going to be equal to L divided by 2. And that will also be in units of meters. The quantity P that we're interested in will be the rho times omega. And then remember, asterisk asterisk is for square, times A times the L times the x minus 1/2 times x, and we'll use asterisk asterisk star. Okay, so we're at L over 2. I mean, we can calculate some of this in our head. This is going to be L squared minus 1/2 quantity L over 2 squared. So this is going to be essentially 3/4 L squared, but we'll go ahead and let Colab do its thing. And it doesn't spit anything out because I didn't print what P is going to be equal to. So P is going to be equal to, this would just give us the unit, the final answer in newtons if I don't do anything to it. So I'm going to do P, let's just do like 1 decimal place, and we'll say newtons. All right, so it comes out to be about, well, about almost 1600 newtons for the internal force. The next problem will build on this script, so don't delete it, and I hope you found this particular problem helpful.